Good afternoon, everyone. Today I'll be introducing, on behalf of my friend from Tsinghua, CoT-LM, a data-free collaborative fine-tuning framework for large and small language models. So pre-trained LLMs have shown impressive general-purpose capabilities across a wide range of tasks. However, they often fall short when applied to specific domains like healthcare, finance, or customer service. Therefore, fine-tuning them on domain-specific data is essential. They require data-specific data, which is often private, usually residing in hospitals, companies, or personal use devices, and cannot be collected to the cloud due to privacy regulations or business barriers. To enable fine-tune LLMs with private data, a widely adopted solution is federated learning. In this paradigm, a pre-trained LLM is sent to the downstream nodes, fine-tuned with their local private data, and then aggregated on the cloud server. However, federated LLM fine-tuning runs into two problems. First, fine-tuning large language models is computationally expensive. Not all nodes can afford it. For example, models like GPT-3 requires hundreds of gigabytes of GPU memory. Second, pre-trained large language models are valuable assets for their owners, so their owners often don't want to share them for downstream fine-tuning due to the IP problems. To address these issues, we propose a new paradigm for LLM fine-tuning. Instead of downloading the LLM, each node trains a small language model with their local private data. Then the small model is used to provide feedback on the synthetic data generated by the large model. With the feedback, the large model is promoted to generate better samples. Then both the large and small model can be fine-tuned with the synthetic data. In this paradigm, the private data stays local and the large model stays on the cloud, which preserves both private data and the property of the large language models. Our system is named CoT-LM, and here is how it works. Each node trains a small local model using its private data. In the meantime, the large language model on the cloud generates labeled descriptive prompts based on the downstream task. It then produces synthetic samples that are evaluated by the small language models. These small language models act as task-specific critics, assigning feedback scores based on how well each sample aligns with the intended label. This feedback is used to guide and fine-tune the large language model, improving its generation quality. In turn, the enhanced LLM creates better synthetic data sets. These synthetic data can also be used to further improve small language models, creating a mutual beneficial loop. Next, we'll introduce the design details of CoT-LM. First, let's walk through a simple example. The system first samples a task label, for instance, positive. Then it constructs a prompt like, here is a positive movie review. And then it passes this to the LLM. The LLM may generate a response such as a good movie. We then append the label into a natural language form, such as a good movie. This is a positive movie review. This entire sequence is treated as a synthetic label sample. But how does the system ensure that these synthetic samples are actually useful? This is where SLMs comes in. For each generated sample, the corresponding SLM predicts the probability that the sample matches its intended label. This probability is transformed into a reward signal, high if the match is strong and low otherwise. We then compute what we call the quality-driven generation loss. The intuition behind the design of this loss is to improve the likelihood that the LLMs generate high-quality text while decreasing the probability of generating low-quality text. Specifically, a large reward indicates the generated data is high quality. In this case, we aim to increase the probability that a large model can generate this text. On the contrary, if the reward is small, it decreases the possibility. Therefore, the design of this loss enables smaller loss values when the LLM has a higher probability of generating high-quality text. We go further by using these synthetic sample label pairs to fine-tune the LLM itself. The sequence, A Good Movie, this is a positive movie review, is treated as a continuous natural language passage and used for self-supervised learning with a language modeling loss. This not only improves the large language model's ability to generate coherent text, but also helps it internalize task-specific semantics. With the above two losses, the LLM can be fine-tuned to adapt to specific tasks. However, there is a risk. If we fine-tune the large language model too aggressively on synthetic task-specific data, we may lose its general-purpose capabilities. This loss constrains the fine-tuned large language model's output distribution to remain close to that of its original pre-trained version. Therefore, serve as a regulation term to limit significant updates on the pre-trained LLM to preserve its generalization ability. Finally, the total loss function for the LLM combines three losses. The generation loss steers the LLM towards higher quality output using feedback from the small language models. The unsupervised loss improves task awareness via language modeling on synthetic samples. The regulation loss preserves the general purpose knowledge by anchoring the large language model's output distribution. We can use scalar weights to balance these components. These hyperparameters are chosen empirically through grid search to ensure optimal performance. It's now our turn our attention back to the small models, the SLMs. After the large language model has been fine-tuned, it continuously generates synthetic data across iterations. We collect these samples and filter them based on quality, using the reward score and diversity, using sentence similarity metrics. These top quality samples are used to further improve the SLMs via standard local training algorithms. In this way, CoT-LM completes a full circle of collaborative learning, enhancing both the large language model and the small language models in a mutual beneficial loop. To validate the effectiveness of CoT-LM, we evaluate it using two widely used large language models, GPT-2 Large and Llama 7B, deployed on the cloud, and two smaller small language models, BERT-based and DistillBERT, deployed on mobile nodes. These small language models are randomly assigned across nodes to reflect a heterogeneous setting, as would happen in real-world distributed systems. We focus on 4 natural language classification tasks: SST-2, IMDb, AG News, and Yahoo. These datasets vary in size, label distribution, and difficulty, which ensures that our framework is tested across a broad spectrum of use cases. We split each dataset using distribution with alpha equal to 0.5 to simulate non-IID setting across nodes. We compare CoT-LM against 5 baselines. The without fine-tuning method directly evaluates a pre-trained LLM on tasks without any adaptation. The self-tuning method uses the large language model to generate task data and fine-tune itself accordingly. The fed-LA method applies LoRa-based fine-tuning on nodes and upload updates for server aggregation. The fed-prompt method freezes the large language model and only tune and aggregate soft prompts. The off-site tuning method shares a compressed large language model version and fine-tunes an adapter on the node. We evaluate 5 key dimensions. The first one is the task-specific natural language understanding performance of fine-tuned LLMs, which is measured by classification accuracy of large language models on specific tasks. The second one is the task-specific natural language generation performance of fine-tuned large language models, which is assessed by how well the generated samples match the label using a pre-trained classifier as an evaluator. The third one is the generalization capacity of LLM LLMs after fine-tuning. We test whether the fine-tuned LLM could still perform on unrelated tasks as shown in Table 3, and also report the perplexity on the Penn tree bank data set. Besides, we also evaluate the task-specific performance of the SLMs after enhancement and the resource efficiency of the collaborative fine-tuning process. Here is the task-specific natural language understanding performance and natural language generation performance of large language models after fine-tuning for various tasks with CoT-LM and baselines. We can see that most baseline methods struggle with natural language generation performance, particularly fed-prompt and fed-LA. In contrast, CoT-LM can enhance LLM's task-specific natural language understanding and generation performance simultaneously. Then, we evaluate the generalization capability of LLMs after fine-tuning. Here, we measure the accuracy of LLMs on benchmark data sets before fine-tuning and after fine-tuning for various tasks. We can see that after fine-tuning with CoT-LM, the accuracy drop of LLM is minimal, while baseline methods show significant degradation. We also measure the perplexity of LLMs on the PTB dataset to reflect its generalization capability. We can see that CoT-LM only causes a negligible change. These results demonstrate that CoT-LM has a minimal impact on the LLM's generalization abilities. Now let's turn to the small language models. Here we compare with two baseline enhancement methods. In the first baseline, the SLM is trained only on its local data without external enhancement. In the second baseline, the SLM is first locally trained, then enhanced using syntactic data from a pre-trained large language model without fine-tuning. We can see that the SLMs enhanced by the CoT-LM outperforms the other two. This proves that fine-tuning large language models collaboratively with SLM feedback result in significant better synthetic data and therefore better downstream models. To understand why CoT-LM performs so well, we conduct an ablation study. We remove each loss component in turn: generation loss, regulation loss, and language modeling loss. The results were clear. Without generation loss, sample quality drop. Without language modeling loss, task understanding suffers. Without regulation loss, generalization collapses. Only when all three losses are present does CoT-LM achieve the balance of task performance and generality we need. CoT-LM also stands out in terms of efficiency. When using a BERT-based SLM, node memory usage is around 3.3 gigabytes. For distilled BERT, it's only 2.3 gigabytes. This is a stark contrast to fed-prompt and fed-LA, which requires 15 to 27 gigabytes per node. Communication cost is also significantly reduced by transmitting compact small language models, avoiding full model or adapter transfers. This makes CoT-LM ideal for real-world mobile environments like mobile phones and IoT devices. Next, we evaluate the scalability of CoT-LM. We can see that as more nodes contribute to the fine-tuning process, CoT-LM shows a consistent upward trend in both natural language understanding and natural language generation performance. We also evaluate the performance of large language models in the continuous fine-tuning process with CoT-LM for various tasks. We can notice that when the large language model is adapting to the new tasks, their performance on old tasks show small decline. This indicates that CoT-LM can efficiently preserve the large language model's previously acquired knowledge. This is thanks to the regulation loss incorporated in CoT-LM. Finally, we address the privacy concern. That is, could someone reconstruct private data from an uploaded small language model? We simulated model inversion attacks using both vanilla generation and text revealer method. Here, we measure the recovery rate, that is the percentage of tokens reconstructed from the private data set, and the perplexity of the reconstructed data. We find that the overall recovery rate is relatively low. Besides, most reconstructed tokens are common and uninformative words. So the perplexity is also high. This indicates that the reconstructed text exhibits poor readability. In summary, we propose CoT-LM, a practical, privacy-preserving, and resource-efficient framework for collaborative large language model fine-tuning. CoT-LM enables bidirectional knowledge transfer and mutual enhancement between large and small locally trained models. CoT-LM improves both natural language understanding and generation capabilities of large language models and scales across tasks and nodes. Thank you.
Questions as well? No.
Yeah, please email the authors.
Yeah. So one question I have for the authors is, why did the name change from CoT-LM to CoT-LM? Do definitely ask them for me.
Yeah, the CoT is cross-chain, so
Oh, okay.
CO.
Oh, okay, so they changed it to CoT-LM. Okay, that's a fun fact to know. Anyway, thank you, Beijing, again, for a great talk. And we'll move on to our second paper.